Good afternoon, ladies and gentlemen. My name is Dr. Andonis Papadakis, and today I will be presenting the results of a project called Real-Life Simulation of Oil Spills using Graphical Processing Units and Artificial Intelligence. The project is funded by the Research Innovation Foundation, as well as the European Regional Development Fund, under the project concept 0722-0066. The table of contents show the outline of the presentation. I will be presenting the project objectives, the KYAMOS software overview, our solutions, test cases, methodology, lattice Boltzmann simulation, and AI-tuned results. I will discuss the results and draw my conclusions. The project objectives is to develop software supporting infinite band GPU computing for oil spill simulations, to conduct experimental proof of concept TRL3 activities in the fields of artificial intelligence and computational fluid dynamics for oil spill simulation, to validate these technologies in a lab environment in KYAMOS premises at TRL4 level to predict instantly oil spills, to benchmark test cases, to conduct a real oil spill scenario and incorporate this technology into KYAMOS software platform. KYAMOS software is a cross-platform software on Linux and Windows. It is a low-cost alternative, yet powerful software. It provides detailed insight into the design process, and we use AI simulations for instant high-fidelity real-life simulations through pre-trained models. There is an automated, secure, and fast client-server communication through in-house daemons. We are currently developing 7 green technologies: those of oil spills, radio frequency filters, electromagnetics, semiconductors, wind turbines, batteries, and thermal. Software properties. Our software is user-friendly. We have ready-made customized modules for non-engineers, simplistic, ergonomic, and friendly GUI with drag-and-drop capability. We achieve high fidelity using weak and strong scaling by choosing the most accurate state-of-the-art numerical techniques according to the discipline, and to provide real-life detailed insight into multiphysics simulations. We provide simulation diversity by offering multiphysics solutions and coupling of equations from different engineering disciplines. And we utilize innovative technologies and target them, such as artificial intelligence, quantum computing, and digital twins due to the fourth industrial revolution. Our software and hardware architecture is as follows. We offer a hybrid software as a service cluster model. We have a GUI software on the client side and the good-aware MPI software on the server side. We utilize optimized parallel practices and libraries. The libraries are Thrust, NCCL, MPI, and CUDA. We exploit memory coalescence in the GPU. We exploit GPU to GPU memory access bypassing the CPU. We build an NVIDIA infinite band GPU server for scaling the simulations, and we exploit fiber optic communication internet speeds with low latency and high bandwidth. Regarding this project, the first one package is the project management. We have weekly meetings to ensure alignment with work package objectives. We identify roles and responsibilities of each team member. We regularly updated our progress for the project, and we plan the project with tasks, milestones, and deadlines. We fostered collaboration and communication among team members via Zoom and emails and in person. We utilize the Samba user to optimize productivity and efficiency for sharing files, and we exchanged information through an email service based on MariaDB database, Postfix, and Dovecat, and including SSL features, spam assassin for spam, and ClamAV for viruses. And the monthly meetings summarize this progress. For WP2, the simulation activities, we have published an open access peer-reviewed scientific journal. We presented the results at an international conference. We are presenting the results of the oil spill software in this video. We created a promotional video for lattice Boltzmann oil spill software. We created a forum for KYAMOS oil spill, and we submitted a request to the services of the CKTO of the RIF. Now, moving to work packages 3 to 9, which are the technical packages. First, in WP3, we conducted a literature review on oil spill simulations and deep learning processes. In WP4, we developed the lattice Boltzmann MRT LES oil spill simulation in software programming C++. In WP5, we benchmarked the lattice Boltzmann solver. In WP6, we conducted a real test case simulation of an oil spill simulation. In WP7, we parallelized the solver using state-of-the-art good-aware MPI protocol. In WP8, we used TensorFlow GPU installation and deep learning training to train a model. And in WP9, we develop a deep learning training validation AI tunet for the OSP model by utilizing Tensor and PyTorch. Our solutions, we offer Optimus Solver. For example, for incompressible turbulent flows, we utilize lattice Boltzmann. For field problems, we use finite element Wigler-Lerkin method. And for compressible flows, we use finite volume total variation diminishing schemes. We use sparse matrix utilization and conjugate gradient for symmetrics and GMRS for asymmetric matrices. We utilize CUDA-aware MPI and GPU direct boost by NVIDIA for boosting our simulations in order to provide real-life insight into simulations. The lattice Boltzmann method has a velocity set of DDQQ, where D is the number of spatial dimensions and Q is the number of velocity vectors. Commonly used velocity sets to solve Navier-Stokes and other partial differential equations are D1Q3, D2Q9, and D3Q19. A desired velocity set must obey the following conditions: conservation of mass and momentum, and rotational isotropy of the lattice. And the discrete velocity vectors are illustrated in the pictures of the velocity sets. Here we see the D2Q9 and the D3Q9. Now, the lattice Boltzmann method, the steps are as follows. We have an advection diffusion equation, and here we have the time-dependent concentration, the advection, the diffusion, and any source term. We have a set of positive weights associated with the discrete velocity vectors EI, and the initial distribution functions are initialized using the equilibrium distributions, which are based on these equations, where W is the weights, rho is the density, U is the macroscopic velocity, CS is the speed of sound, and EI is the velocity, discrete velocity vectors. Now, the lattice Boltzmann has a series of tests to be completed. First, we perform a collision as follows in order to calculate the post-collision operation. And then we perform a streaming, which is the propagation, according to this equation. Then we apply the boundary conditions. We increase the time stem from t to t plus delta t. And then we compute the macroscopic moments, such as density and velocity, by using the sum of the densities and the sum of the densities multiplying by the weights. And we incorporate then external forces or source them, if applicable, into the simulation. In our case, this is the oil field simulation. And we obtain scalar fields and repeat these steps for a desired number of time steps. Our test case is a two-dimensional solver. Our computational domain is a square shape 40 by 40 lattice Boltzmann nodes representing the seawater with an oil spill starting from the left bounded to the right. We take values such as the density of the crude oil, 800 kilograms per meter cubed, the density of the seawater, 1000, the initial seawater velocity, 0, the inlet velocity of seawater on the west boundary, 0.1 meters per second, area of the oil spill, 20 by 20, mass flow rate, 1, inlet velocity of oil spill, as I said, is going to be 0.1 meters per second, diffusion coefficient of crude oil, 1 times 10 to the minus 5, and the kinematic viscosity, 1 times 10 to the minus 6. Our methodology, the key steps of the procedure involve consider turbulence behavior by using large eddy simulation based on the Smagorinsky subgrid scale model to calculate the small eddy, obtain the density and velocity fit in the whole domain using a D2Q9 model, retrieve the outcomes of the lattice Boltzmann simulation, and employ them as inputs to the AI tunet model, and adjust the model parameters for accurate predictions. Some of the work done, we conducted a literature review on the lattice Boltzmann method for oil spill simulations, demystified the D2Q9 formulation for oil spill collision and streaming, and we implemented boundary conditions for inlet, outlet, slip, and no slip. We devised a partition scheme for lattice Boltzmann nodal-based simulations. We conducted the lattice Boltzmann GUDA simulation and implemented the LES model based on Smagorinsky for oil spills. Here, as we can see, we discretize the D2Q9 lattice Boltzmann MRT model, creating a uniform square mesh, and solve the advection diffusion equation. In order to scale our model, we needed to conduct mesh partitioning, and this is created by an algorithm created in-house for the lattice Boltzmann mesh. It is nodal-based, and we used MP-MEDIS, but it couldn't be balanced. So we created, in order to create contiguous partitions, so utilize alternatives such as the M2G MEDIS for graph creation and GP-MEDIS for mesh partitioning. The process involved node splitting communication for shared nodes. We conducted local mesh renumbering, and we created an IP by duplicating nodes for lattice Boltzmann using the MPI all-to-all operations. Now, regarding the AI unit, it's an image segmentation technique segments and extract important macroscopic features from 2D and 3D simulations, i.e. speeds, pressure, temperatures, energy, velocities. It has the ability to handle large data sets and multi-class segmentation problems. It partitions the mesh into multiple segments, with each segment corresponding to a different region of the image, and deals with small training data sets by using data augmentation that involves applying various image transformations to the input image and the corresponding segmentation masks. Some properties of UNet: it is based on convolutional neural networks. It consists of an encoder-decoder architecture. It is fully based on convolutional principles, avoiding fully connected layers. The utilization of key connections enables it to learn robust features and refine the segmentation boundary based on detailed information from the input image. Here is a structure of the unit. We can see on the left the encoder and the decoder. And here we can see the various layers. And we can see here the channels slowly increasing from 3 to 64 to 128, 256, and 512 in the encoder. And then, while in the decoder, we decrease the number of channels from 1024 to 512 to 56, 108, 28, 64, and 3. And here we can see the various operations such as copy and concatenate, convolution plus ReLU, maximum pull, upsampling, convolution, and final convolution. The advantages of UNet: UNet can capture effectively complex flows and heat transfer phenomena by handling large and complex datasets, while at the same time handling multi-class segmentation problems. It is an ideal choice for CFD analyzing and for optimizing phenomena, and it can capture and predict the result of fluid flows, i.e. of the density, velocity, and pressure, with the emanating errors being acceptable for fluid flow simulations. Now, we had a breakthrough, the time UNet or 2net. We added time in UNet as an input variable. The time sequences were captured. We conducted 68 simulations of oil spills with 27 time steps each. The image size was 101 and 101 pixels. The output time was outputted every 10 steps, time steps. And 1,836 files for each input and each output variable were used, and the total files were 8 times 1,836, a total of 14,688 files. The parameters that were used were the learning rate 0.001, the batch size was 64, the epochs 1000, and filters 81632. Now, we used 5 input variables. The first one was time, second was initial horizontal velocity, third was initial density of crude oil spill, fourth was the boundary condition classification index, and number 5, the horizontal distance from the inlet velocity. And for the output variables, we have used 3, the horizontal velocity, the vertical velocity, and the density of crude oil spill. Some of the results of the 2net, here you can see in 3 rows, the velocity in the x direction, the velocity in the y direction, and the density of the oil spill. Here we present the results from the lattice Boltzmann MRT, CFD, in this column. This is the 2net prediction, and this is the error. And we can see that there is a close agreement within the results of the order of 1%. And it is able to predict the oil spill very well, as well as the velocity of the UX and the UY at a very good and satisfactory resolution. Here we can see a video of the benchmark oil spill speed. We basically apply an inlet velocity on the left boundary of 0.1 with 0 velocity inside the seawater, and we create basically slightly compressible shock. And we calculate, for example, the velocity, speed, acceleration, and we see that the results of the lattice Boltzmann are similar to the theory and agree well. As you can see, as the velocity reaches the right boundary, it basically bounces a little bit back and stays constant at around 0.1 meters per second as we move along. Then afterwards, here is the oil spill. We just release a small oil spill on the left, right on the left, just outside the inlet velocity, and you can see that slowly, the oil spill of the crude oil, which was only initialized and then kept constant, starts to spread, and at the same time moving from the left to right, according to the sea currents coming from the inlet velocity. And you will see that its density is dropping due to the fact that it's traveling and spreading at the same time. For example, you can see that it is at a value of 0.40 maximum value. and slowly it spreads out in our domain and decreasing its density value. Here is a more realistic approach of an oil spill. Here we can see an inlet velocity which varies sinusoidally from left to right from an oil spill that was created between the small island and the oil spill. And you can see that the speed which is created due to basically the wakes which are created along the small island, which is according to what is expected. And the velocities, you can see they vary up and down because of the sinusoidal nature of the inlet velocity. There is a constant mass flow rate right here, which is released due to a continuous oil spill from a tanker that was simulated realistically. And finally, the most important result is we can see here is the inlet velocity, here is the mass flow rate, which represents the oil tanker oil spill around the small island. And you can see that how the oil spill accumulates around the boundaries of the island, as well as propagated inside the sea, following the velocity of the seawater. And we can see the wakes changing directions, sometimes moving upwards, sometimes moving downwards. So in order to proceed, we needed to do a Cyprus digital map. So we used software called QGIS, and we loaded 3 layers, the Cyprus, Northern Cyprus, and Akrotiri, and the Geia layers. And the map layers were loaded and combined and merged into a single layer using vector data management tools, merge vector layers. Then we generated points along the geometry using vector geometry tools, points along geometry. And then the layers were dissolved in QGIS. The points to path option was used to create a single polygon. And any problematic points were manually removed using toggle editing, and points to path was revisited until success. And the coordinated degrees were extracted for further processing in Python. Then we use Python to convert it into SI units, and also use Python to normalize it in SI units. And then we developed a C++ winding sum algorithm to identify inside nodes by which returned 1, on boundary which returned -1, and on outside points which returned 0. And the result was to be able to capture the digital map of Cyprus. You can see here blue circles represent onshore and red crosses represent offshore. So we have the capability of having the digital map of Cyprus for running oil spill simulations. For our discussion, we have already developed and tested an efficient partition algorithm which takes full advantage of GPU acceleration. We developed and tested the 2D lattice Boltzmann MRT for a regular domain with an oil spill. We enhanced the 2D lattice Boltzmann MRT solver and benchmarked it, demystified the AI2Net model, and we adjusted the AI2Net model and evaluated its performance in 2D. Future way is to implement the 3D lattice Boltzmann MRT solver and benchmark it, adjust the AI2Net model and evaluate its performance in 3D, basically as a VNet model. Consider solving multiple oil spills at the same time. In conclusions, real-life simulations of oil spills are successfully implemented. The lattice Boltzmann MRT 2D produced logical results. The AI2Net predicts the oil spill with 98 to 99% accuracy. The focus will be on providing practical solutions to industry, including 3D solutions and considering multiple oil spills. And our aim is to contact ExxonMobil as potential customers and capitalize on our results based on expression of interest letter that was secured before the submission of this proposal. Thank you very much.